I want to cover the Lab9 2D flow problem. Specifically, I want to explain how to take the flow rate that we measured in the lab and convert that to the flow rate you'd expect in the field. A number of you had trouble with this in the lab write-up, so I thought I'd go over it. Now this is the flow net we have for the problem. And since the lab model is the same geometry as the field model, the flow net is the same in the lab or the field. Or another way of saying that, it doesn't matter what scale I do this to, whether I measure this in inches, centimeters, feet, meters, or anything, the actual flow net itself doesn't change. So the flow net is the same for both the lab and the field. And if the flow net for the lab and the field is the same, I can write the equation for the flow in the lab, Q sub L, as delta H in the lab times K, the hydraulic conductivity in the lab, times the quantity N sub F over N sub D times B over A in the lab times the length of the problem in the lab. That's actually the length into the paper. And similarly in the field, I can write the Q sub F in the field is equal to the delta H in the field, the change in head, times the hydraulic conductivity in the field, times N sub F over N sub D times B over A in the field, times the length of the problem in the field, into the paper. Now, the hydraulic conductivity is the same as in the lab or in the field, because in the lab we use the same soil that we're supposed to have in the field. And if the flow net is the same in the lab or the field, then these two quantities are the same in both the lab and the field. So knowing that, I can combine these two equations to determine that the flow in the field is going to be equal to delta H in the field times L in the field divided by delta H in the lab divided by L in the lab, all times Q in the lab. So that's how we relate the lab flow rate to the field flow rate. So let's compute that for your problem. Here's the problem we have. This is delta H, and in the lab it's equal to 18 centimeters, and in the field it's equal to 18 feet. The length, that is the width of the flow problem in the lab, or the length into the board, is 10 centimeters in the lab. And in the field, it's 150 feet, because remember the length of the cutoff wall is 150 feet. So we then can write that the Q in the field is equal to this delta H in the field times L in the field divided by delta L in the lab divided by L in the lab times Q in the lab. Same equation we just derived. So that's going to be equal to 18 feet times 150 feet divided by 18 centimeters times 10 centimeters times Q in the lab. We can simplify that a little bit. 18s will cancel out. We can take the 10 and divide it into the 150 and get 15, and we'll have that the Q in the field is equal to 15 feet squared over centimeters squared. Now I've got to do a conversion here to get rid of these units because that quantity needs to be dimensionless there. The 15 quantity needs to be dimensionless. So I'll recall that there's 2.54 centimeters in an inch and 12 inches in a feet, and if I square that, the inches squared will cancel, the centimeters squared will cancel, and the feet squared will cancel, and I'll have a dimensionless multiplier there times Q in the lab. And if I multiply that out, I'll get that Q in the field is equal to 13,935 times Q in the lab. But now remember, there's actually two cofferdams in the field, one on each side of the excavation. So we actually have to multiply this number by 2 because we got flow coming in from both sides in the field. And so the Q in the field is going to be 27,870 times the Q in the lab. And if you look at your data from the lab, we measured that the flow in the lab was about 0.371 gallons per minute. I multiply that by 27,870, and I'll get that the Q in the field that we expect is 10,340 gallons per hour. Now, a lot of you computed a flow rate that was like a few gallons per hour, and you should know, it should have been obvious, I think, that in the field you're going to have more than a few gallons per hour flowing into the excavation. But that's how you do the problem. You just need to use dimensional analysis to get the answer. I hope this helps.